Hello everyone. In this video we're going to look at the second section of Module 1, Probability Rules and Independence. In this section we're going to learn about these three main rules of probability: the addition rule, multiplication rule, and the total probability rule. And among these topics we will learn about these two very important topics of conditional probability, where calculating probability is going to get a little more difficult, and independent events. And you can learn about these topics in these sections of the textbook. So let me first remind you about the ruled wheel example. And I want you to remember these letters and what they represent. In the ruled wheel example, we have 38 outcomes, zeros and double zeros, and 1 through 36 are the outcomes that we have. And we define these events, which are basically subsets of the entire sample space. Red outcomes, black outcomes, odd, even, first 12, second 12, third 12, and green spaces, which represent 0 and double zero. So with that in mind, I want you to think about this question. Is probability of R union T1 equal to probability of R plus probability of T1? And I want you to pause the video and work on this and see if this statement is actually correct. You need to calculate probability of R, T1, and then find out what are the outcomes in R union T1. Then calculate the probability of R union T1 and see if this is equal to the summation of these two. So let's take a look at these probabilities here. Let's start with the first one, probability of red. We know that in the ruled wheel we have 18 red outcomes, and you can count them and you see that. So probability of red will be 18 over the total number of outcomes, which is 38. Probability of T1, well, we know that T1 is the first 12 and there are 12 outcomes in there. So the probability of that will be 12 divided by total number of outcomes, 38. What are the outcomes in this event, R union T1? Well, we know red and we know T1. What is the union of those two when you put them together? Well, T1 is 1 through 12 and R is all the red outcomes. So if you put them together, what are those outcomes? Well, it will be definitely 1 through 12, and all the red outcomes outside of first 12, right? 14, 16, 18, 19, 21, all the way to 36, all the other red outcomes. So I would just write down reds outside of T1. And if you count them, this is 12. And then we have 12 more. So in total we have 24 outcomes. We can double check this on the ruled wheel in the previous slide. Well, now that we know we have 24 outcomes in this event, what is the probability of this event? Well, it's going to be 24 divided by total number of outcomes, so 38. Now, is this a correct statement or not? Well, the answer is no, it's not. Because on this side we have 24 over 38, and this is not equal to 18 over 38 plus 12 over 38. In fact, this is 30 over 38. So it's not true. So keep that in mind and think about what needs to be added to this equation so it becomes a correct equation. Well, the piece that is missing here is minus probability of R intersection T1. Because 30 over 38 double counted the intersection area. If you look at the ruled wheel example, R intersection T1 is 1, 3, 5, 7, 9, and 12. We double counted them when we were calculating the right-hand side of this equality because we once counted them here and we counted them here twice. So in the union, you shouldn't be double counting them. So if you want to have a correct equality statement here, you need to subtract probability of R intersection T1, and then these two sides will be equal. And probability of R intersection T1 is there are 6 outcomes, so 6 divided by 38. And then this equality will be correct. It would be 24 divided by 38 here, and then 24 divided by 38 here as well. So that's the basis of the first rule that we're going to learn, and that is the addition rule. The addition rule says for any two events A and B, probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. And keep this in mind, this is true for any pair of events, including mutually exclusive events. And you can rearrange this formula to find any of them if you're looking for any of them that is unknown. That's the addition rule for two events. The same rule can be extended to 3 events or 4 events. It's the same idea. I actually encourage you to draw a Venn diagram and test this part. Now draw a Venn diagram with A, B, and C, right? And see if this is correct. Probability of A, B, and C together. That's that part plus that part plus this part minus A intersection B, A intersection C, B intersection C. And that is because we double counted these areas. So we subtract them. Once we subtract these areas, we entirely wiped out this little area in between, which is the intersection of all of them. So we have to add that at the end. And the same logic can be applied to 4, but that's beyond what we are going to focus here. So that was the addition rule. For when we have a mutually exclusive collection of events, right? Let's say we have 10 different events that are mutually exclusive, which means they don't have any intersection area. For example, in the roulette wheel example, red, black, and green is a set of mutually exclusive events. They don't have any intersections. There is no outcome that is both red and black or both green and black or anything like that. So they are forming a set of mutually exclusive events. In those cases, let's say B1 through BK is a set of mutually exclusive events. Probability of their union is equal to the addition of probabilities. Probability of B1 plus probability of B2 all the way to probability of BK. You don't need to worry about any intersection area here because there is no intersection. And the left-hand side of the statement is basically probability of B1 union B2 union all the way to BK. A special case for a set of mutually exclusive events is when that set covers the entire sample space. So if we have a mutually exclusive collection of events B1 through BK such that their union is equal to the entire sample space, we call it partition. They form a partition. That's what you see in this Venn diagram. This A, B, C, D, E, F, they don't have any intersections with each other, and they form the entire sample space, as you can see. There is no area in the sample space that is not covered by them. So A, B, C, D, E, F, they form a partition. So that's the definition of partition. In the next video, we're going to look at one example and exercise what we learned.